So about 20 years ago, a group of leading FEA researchers decided that, again, given this current status of how FEA is just not integrated into CAD, could there be a better way? Could there be a way of, rather than spending up to 90% of the overall time to solution in just reworking the data and then running a simulation on something less accurate than the CAD, and then having it be difficult to go back to the CAD because there's no straightforward way to add the insights, and the whole point of running analysis anyway is to improve the design. But if it takes so long that there's no time to improve the design, it's just this pass-fail at the end of the product design process, we're really underutilizing the value that could be driven from finite elements. So people have tried to come up with new CAD representations for various reasons. The interesting thing is, though, that of all of the new CAD representations that have come out in the last recent years, I mean, NTOP's been one that's been mentioned today as well as others, no one has picked finite element math as the basis for creating new CAD software. And the reason is because finite element math is good for really nothing besides finite elements. So there's, to kind of pick your poison with how you represent finite elements, you can either use hex meshes, which are the most accurate and performant and robust, but the only problem is it's a very manual process to create these. At best, it's semi-automated. And so that's kind of on the one side. The other side, you can use tetrahedra, which can be automatically generated, but they can be very expensive to compute because of the element quality. So to get the automated ability to add these tet elements to fill up a volume, you sacrifice the aspect ratios. The Jacobians are much more poor, and that just leads to a less predictable and a longer solve time. So since no one's picking FEA math to make CAD, what if we flipped it and said, well, what if an FEA code could be created based on the mathematics of CAD? So that's what we're doing at Coreform. This is part of a larger field called isogeometric analysis. These papers were first published about 20 years ago. There's been over 4,000 papers now published exploring the idea of using CAD math as a basis of FEA. And it turns out that these higher order smooth spline basis functions that are used to define CAD are actually more accurate, more robust, and better behaved than the traditional Lagrange elements used for FEA. And so it's really creating a new solver that's based on the superset of the technology that was first implemented in Astra in 1965.